today, so instead you guys got me. Hans Cross with Oceaneering, been in the industry with Oceaneering for 14 years, going on 15. My entire career has been involved only in deep water, and specifically in intervention tools and operations, typically complex operations. What we're going to discuss today is rigless well stimulation, but specifically deep water. That means wet trees. So that's different than the traditional setup where you have a floater platform with dry trees or a surface platform. Specifically, we're not going to discuss so much about what happens with the stimulation work itself. It is more on how to perform this riglessly with multi-purpose vessels. These well intervention services are part of a program called Ocean Next within Oceaneering. Ocean Next performs complex operations that span multiple business units within the organization. So it really focuses specifically on well interventions, flow assurance, well interventions that have to do with well stimulations, flow assurance, of course, hydrates fall under the flow assurance purposes. So, well stimulation falls under a category called hydraulic well intervention. How do we perform these well interventions without a drilling rig? Sorry, I got a database update message. How do we perform these stimulations hydraulically without the use of a drilling rig? The result of this stimulation, pardon me, quick adjustment here. It's eliminating the cost of a drilling rig is the importance here, and you perform this with an MPSV, a multi-purpose service vessel outfitted with multiple ROVs and a subsea crane. That's the typical platform that these types of campaigns are used on. Furthermore, the liquids or the chemicals are delivered to the seabed via open water coiled tubing risers. Those are those vertical lines that you see there. And then, of course, finally, when you get down to the subsea tree, you have a well intervention tool or a simplified well isolation device. So, blowing this section up here, you have a subsea tree in deep water. On it, you have a means of latching onto it, and then you have your hydraulic coiled tubing units running over to the surface for delivering the liquids or the chemicals. We refer to this system here as a WSD, as a well stimulation tool specifically, but it could be a means of different forms of isolation devices. Traditionally, how it's performed is we have multiple cases that we operate this well stimulation tool. Several operators have a preference on how it's performed, and also regulatory has a preference as well. What we'll go into it with here is specifically focusing on the technical aspects of making it safe. That's the important part of this. So here you see an isolation device sitting on top. Here's the same isolation device sitting off the side of the well, and there you have the same isolation device again sitting on top of the well, but instead it's performing its injections through an alternate means. Might it be a flow connection or a choke insert. So again, liquids are stored on board the vessels. Pumping is delivered on the vessel. You have what's not shown here is multiple ROVs and crane as well. So this is your multi-purpose vessel. Then from there you have a riser. We call it a coiled tubing riser, but it might be a flexible as well. And finally, you get to your working depth, which might be, in deep water, might be 6,000 feet or more. and there you have your isolation device on the seabed. This isolation device there is controlled by the vessel, and the tree is controlled by the vessel as well. So typically, the subsea tree is controlled from the host. In this operation, this is performed from the vessel, so that the control is taken away from the host and performed remotely by the vessel. There's a reason why there's multiple ways of performing this. And in some cases, it might be an asset issue. There might be these interface issues that are not available, and therefore we might deploy the well stimulation tool on the seabed. Why it's important that the well stimulation tool resides on a strong foundation is that in one of the safety cases, if there's a complete blackout on the vessel and the vessel experiences a drift off, this device here, this entire device down here in the seabed must remain safe. In order for it to remain safe and you have a drift off, there must be releases that occur, and ideally multiple forms of safety barriers in place. In this case here, this has to be an anchored device, a strong anchored device. So in this case here, there's either a mud mat or a suction pile placed on the seabed. The well stimulation tool resides on this firm foundation, and that ensures that the jumper going from the suction pile or from the well stim tool over to the tree remains untensioned. It will not be able to impart a load on the remaining of the subsea assets. So in case if there is a drift off, this remains firm and the breakaway occurs above the well stimulation tool. Alternately, this can be performed directly on top of the tree as well. The tree has a built-in anchor on there, and that's a tree mandrel. That's typically used for drill rigs to latch onto, and if a drill rig experiences a similar event, these are very, very strong. They're intended for multi-million pounds of side load to withstand that. So this is called an H4 connection in this case, and an H4 connection adapter will be installed on the well stimulation tool. It will be then injected directly through the H4 connection into the well bore. And of course, the same, all the previous apply. If there is a drift off event, the breakaway occurs on the top, and isolation performs at the top, and therefore nothing below here is subjected to any additional strains or loads. Lastly, here you have an alternate means. Depending on the configuration of the tree, you might have a vertical tree or horizontal tree. A horizontal tree requires that you have that you remove the crown plugs from it before you can attach to and perform a hydraulic intervention. So in those cases, you require a drill rig to perform that operation, or more costly well intervention equipment. In those cases, you could perform a stimulation by going around them and performing a stimulation through the choke or flow line connections. So on this side here, you have a jumper exiting, and here you have your choke insert, and that you can inject through. Excellent. Here's a quick animation. This animation shows the well stimulation tool on a mud mat placed on the seabed nearby the tree. The ROV performs all of the connection work to the tree of from the well stimulation tool. You have one jumper going over to the tree, and then you have your cold tubing risers attaching to the well stimulation tool as well. Communication to the well stimulation tool is performed in several ways. It must be redundant, so we performed it via an electrical conduit going to the surface, so you have communication with it, and acoustically. If one of them fails, the other one remains active. Here you have one coiled tubing riser, and then here shortly comes the second coiled tubing riser. Both are attached to it. We prefer operating with 2 coiled tubing risers. It increases your flow rate, and also it allows you to flush your coiled tubing risers in advance back to the surface to ensure that the chemicals you intend to place into the wellbore are of high concentration, not diluted. So here you have an image of the material being flushed back over to the surface. Once it's all spotted and clean, then we open up the valves here and perform the stimulation into the subsea tree, down into the wellbore. These operations typically last, once you're into the pumping scenario, operating in the order of a half a day to a day. Great, so system architecture. This system here is performed in multiple ways. Traditionally, it's been performed via one vessel. That means all of your liquids, all your chemicals are stored on this vessel. Pumps, intensification pumps, are stored on the vessel. And then, of course, your coiled tubing risers go into the seabed. Sorry, it's a little hard to display here. What does it look like in real life on a vessel? You have all portable tanks, in this case, stored on board the vessel. In this case, you have flammable chemicals, in some cases where you have the wellbore that's causing you issues. In this case, it was xylene that had to be pumped down, so it's very flammable material. So in order to keep all of that safe, additional fire protection and spill response is built into the vessel as well. Dual ROVs interfacing with the well stimulation tool subsea. It's illustrated here with the well stimulation tool landing directly on top of the tree. In blue, it shows the liquid path, and of course, storage tanks on the surface, intensification pumps, and these pumps can be in thousands of horsepower, and then can inject in the order of typically 4 to 8 barrels a minute at 15,000 psi max. Runs down to the seabed. From that point on, you have flying leads. Flying leads are flexible, so it allows you to have some compliance. So the vessel has a little bit more freedom with its station keeping capabilities. Once you reach the well stimulation tool, you go straight down into the wellbore and perform your stimulation, just like any other any other stimulation operation would have happened in the past. In other cases where the liquid requirements are too high for a vessel, particular vessel, you might have to do this with dual vessels. In that case, you have dual dynamically positioned vessels that reference off of each other. One vessel references to the seabed, the other vessel references to the primary vessel. Then you have a liquid carrying vessel, and that liquid carrying vessel might be a stim boat, and that stim boat might transfer the fluids across to the MPSV in 2 ways. One, it could be done in high pressure, utilizing the stim boat's pumps on board. Alternatively, the pumps can still be installed on the MPSV. Liquids are passed on to the MPSV in low pressure, and pumps on board the MPSV then intensify it. So here you have a campaign that was performed in Ghana where 5 wells were stimulated in one campaign. You had a stim boat on location, and there you have the MPSV, again, multiple ROVs, subsea crane, and in this case here, the stimulation was performed with high pressure between the 2 vessels. So this vessel here intensified the pressure to 8,000 psi or so through a coflexive hose over to the MPSV, and there brought on directly onto the coiled tubing risers and manifolds running down to the seabed. And in this case, you show here the well stimulation tool placed on a suction pile as well. So 2 means of performing it with vessels. If your requirements are too high for liquid carrying, then you would rely on on a secondary stimulation vessel or a supply vessel outfitted with tankage. Well stimulation tool. A little bit about its safety case and how it's performed. The well stimulation tool acts as a primary barrier. The subsea wet tree is the secondary, is an alternate barrier. So in order for that to be performed, you must have two barriers within the system. So starting from the surface, you have your coiled tubing reels here, coiled tubing risers going to the seabed. This is the hydraulic circuit for the well stimulation tool. Accumulation built onto the system, preset for the depths that you operate. Here you have two, what we call junction plates, ejection plates, for ejecting the flying leads of the coil tubes if there's something that requires an injection. This ejection can be triggered in multiple ways, and we'll discuss that a little bit more here shortly. And then finally, so in red is the fluid path, the stimulating chemical fluid path. In yellow is your accumulated circuit. And in green is the circuit for triggering the hydraulic circuit to release. In blue are the electrical signals and acoustic signals for communicating to this tool and triggering these, the health checks and the releases. So where you see little waves, those are the acoustics. And then where you see the other blue line, that's the electrical system that is set for triggering the devices. In this case here, pressure monitoring is outfitted on this system, run up to the surface where it's monitored. The acoustic system relays the same thing, therefore it's redundant. Again, multiple barriers built within the system. Here you have your multiple barriers, one right here, second right there, so that if there is a case of shut-in, both barriers are set automatically. Then this system here jumps over to the subsea tree and the choke insert. So you have now the jumpers running over to the tree, and over here you have another flying lead that is able to be made up and ejected as well. Now we're going to talk about the safety case of this whole system. So a lot of words are going to come to you, hopefully you can follow, but the intent of this is to show the different steps that we take to ensure that the system stays safe in case of emergency. So the system contains, the well stimulation system acts as a primary barrier. The reason why is this system you can test on deck prior to deployment. Therefore you're assured that the system is operable and you don't have to rely on subsea hardware that has been subsea for a long time. The subsea tree is considered auxiliary at that point. So therefore, if there is an issue, this is equipment that you can retrieve back to the surface, you can maintain, you can work on. The tree valves are traditionally controlled from the host, might be the platform. In this case here, during the intervention, the regulatory prefers that the operation is controlled from the remote location, i.e. the MPSV, where you have control from. So the tree has a hydraulic system installed is basically teed into the system, and we have the ability of communicating with the tree via a remote control system called a mascot. Tree is typically what it's called. Therefore, we can control the primary valves on the tree, the master valve and the wing valve. So during an emergency disconnect, we can control those valves on the tree. Then, on the entire system, top to bottom, there's 5 levels of emergency shutdown. So there's multiple redundancies built into the system. And then there's a requirement that it is performed without human intervention as well. So in case there is a blackout where there's no control left of the system, this whole system can make safe without the means of human intervention. So we're going to run through cases here of the emergency disconnects, and then we'll refer back to the system in a hydraulic function, and I will run through those. I might have to refer back and forth to pictorially show this to you as well. But if there is so there's in this case here 4 means of making the well stimulation tool safe, triggering the barrier valves to close. The first one is it's triggered due to a loss of station keeping. With dynamically positioned vessels, you can have runoffs and you can have high current events, weather events that can cause runoffs or loss of station keeping. The second is manually from the surface, that is a human intervention. Third is by ROV. The ROV physically intervenes and closes valves. And then last is when all fails, the entire system disconnects by a tension pin. So how is this all performed? So it must be completely automatic. The well stimulation tool barriers close automatically. So therefore, that's why there's a lot of accumulation built into the system. They're triggered remotely and then shut both barriers in and eject your flying leads to the coil tubing risers. The tree is closed. The EFLs going back to the coil, those are ejected. If nobody's watching the pumps that are injecting the fluids, when the pressure spikes beyond a design limit, again, the pumps can be made safe and trigger an ESD. And then finally, communications between if there's multiple vessels, communication between the 2 vessels on shutting down the pumps on the slave vessels, how it's called. Lastly, in the case of a complete uncontrolled disconnect, should a loss of station keeping control occur where none of the above were able to be occurred, finally the system will load a release pin under tension and then shut everything in and still have all maintained containment. So how does this perform with the tree, and how do we have control of the tree? Not only do we have communication, electric communication with the tree, but we also have hydraulic control with the tree as well. Hydraulics still resides from the host, but we have a T, as it were, into the system that is able to release a junction plate, gets ejected at that point, and then vents just the hydraulics in this tree. It's the low pressure system in the tree, and therefore the barriers on the tree trigger themselves. So the acoustic system, in addition to that, along with the coil, are electrical leads running to the seabed as well. Those are for communicating. This one here specifically communicates with the tree up to the surface where your tree control module is located, or a mascot. The second one is the acoustic system and electrical control of the well stimulation tool. So that runs and communicates with the well stimulation tool. So married to the coils are 2 independent electrical lines that control both the tree and the well stimulation tool. And in addition, you have a redundant system that's acoustic. Once this is triggered to disconnect, or this one triggers to disconnect, this one being your primary, it then triggers the junction plate to be ejected, vent low pressure circuit, barriers close, junction plates or EQDs are ejected from there as well. And lastly, a tension cable between the two, called a dead man, is able to trigger all the same disconnects as well. So we talked about the ESD sequences, and we'll talk about all 5 of them that we have in the system here. In the case where there is an overpressure, step back real quick, there is inherently a large pressure differential between the fluid that's injected topside and the fluid that is injected at the wellbore. The difference being hydrostatic head, and the difference being friction loss across the entire system. The coil tubing risers that are utilized typically have a large pressure differential built in due to friction. The faster you pump, the higher your friction loss. So therefore, there's a big differential in pressures. Both those pressures need to be monitored subsea and topside. Should there be a case where one of them runs above its design limit, then there's a means of intervening and shutting down the system. So in this case here, should there be a surface overpressure, i.e. if your system is designed for 15K and your pumps are outrunning your 15K design system, there's triggers on board that will then place the pumps in neutral, and that's automatic without human intervention. Then the system is looped back into the tanks and returned. So the valves on board the vessel are turned around and looped back to the tank. And then lastly, manually, the operator on board the vessel shuts in the tree after you have a pressure event. Second, what if there is a subsea overpressure event that occurs? If you recall in the schematic, there was a pressure transducer installed on the well stimulation tool. If it detects that there's an overpressure event that occurred, it's time to shut down the system and have to assess what's occurred. So therefore, we have to perform a disconnect as well, or an emergency shutdown situation. In that case, same thing, via electrical wire up to the surface, the command is reached and automatically places the pumps, the injection pumps in neutral. Secondly, the valves are isolated on board, downstream of the pump. Manifolds there shuttle and isolate the coil tubes. Then the operator shuts down the tree. Finally, close the barrier valves on the WST manually. No need for an automatic shutdown in here. So manually trigger the shut-in on the WST, but do not eject. There's no need to eject. And then finally, manually via the mascot, the operator shuts in the tree. Same situation, however, the redundant means is acoustics. So if there is an overpressure event subsea, the acoustic signal system is capable of doing exactly the same thing. The well stimulation tool acoustically sends a signal to the surface and automatically places the pump into neutral. Automatically, the manifolds on the surface are closed and the coils are isolated. Manually close, initiate an ESD shutdown on the WST. And then lastly, isolate the barriers on the tree. Fourth case is, what if downhole experiences an overpressure event? If that occurs, then shut down the tree, manually shut in so this is performed by monitoring the mascot system, the computer system that's on the surface, and see that an overpressure occurred, so manually trigger the tree to close its valves, manually trigger the pumps to go into shutdown, In the case this doesn't happen fast enough, then ESD1 will trigger because you just isolated your tree, pressure will spike on the surface, and therefore, without human intervention, you perform a pump shutdown on the surface as well. So ESD1, back to the previous slide, being this condition here. Lastly, if there is a loss of station keeping on board the vessel. Again, these occur in weather situations, loop currents, cold fronts, bad weather situations, thruster failures, or lastly, just a generator failure on board a vessel. If that worst case scenario occurs, then there's an emergency disconnect in the system. So initially, this system is designed, this project would be designed for a specific water depth. That specific water depth has an ability of X amount of feet of horizontal displacement of the vessel. Once that is triggered, once that is reached, the deadman cable tensions up. Once it tensions up, it triggers the WST to perform a shut-in and an emergency disconnect. Additionally, it can be triggered acoustically and electrically. So if nobody's watching, this would work. If it's being intervened by a human, then it can be performed topside by the computers. The result of this is the well stimulation tool ejects its junction plates or the coil tubing connections. The WST commands the tree to vent, and therefore the tree will isolate its barriers on its low pressure circuit. Then this here would be the tree valves closing. Then the WST will eject its EFLs. Lastly, the pump that's still running out of control on the surface spikes. Once it spikes, it performs a trigger on the surface. So this system here can be triggered completely without human intervention. Going back a few slides, we spoke of the deadman cable. Once the vessel drifts off by a predetermined distance, deadman cable tensions up, forms a disconnect. Alternatively, if the people are watching and trigger a disconnect, it's performed from here, acoustically and electrically. And then this system, this junction plate is ejected, tree is vented, barrier valves on here are closed, barrier valves on here are closed, and the EPD connections are driven off. So what does that result in? So the results are actually, we typically find that the results are better than they've been performed by a drill rig. In some cases, we find that what the drill rig have performed in a stimulation intervention just a few months before, we've been able to come back and perform it at a higher quality, better results. We don't know exactly why, but we do believe that it has something to do with the system that we pre-flush. You saw in the animation that we pre-flushed the coil tubes completely, so there's no dilution effect occurring, and therefore the liquids that you deliver down to the well where you can spot accurately and you can treat exactly to the elevations that you're shooting for in your perforations. So in this case here, 5 well campaign that was performed earlier this year. 4 of them were acid stimulation and 1 of them was a scale squeeze. This being the large one where 16,000 barrels of liquid were pumped down the hole. And typically the other wells with acid stimulation are in the order of 2,500 barrels of ejection. Performance. As you see here, on those 5 wells, here's the results on productivity increases. A delta of 1,400% improvement on PI is impressive. 400% improvement. So those are very high and very impressive. This 9% here, this was more a maintenance operation to prevent scale from forming in the future. So that's why the number is quite low. The Ghana example I used a little bit earlier. Here's a timeline of the campaign. This being the campaign. This is the entire production of the host leading up to the campaign. And as they brought wells online, there was always a steep decline almost immediately after. And again, here, as more were brought online, a steep decline occurred. Here, a rig-based treatment occurred, and that's here. You saw a quick spike in production, and then all of a sudden, same decline rates again. And then here finally is the post-acid stimulation in a rigless manner, and the results have been very good. On another campaign, here you have multiple wells. Here in the Gulf of Mexico. In brown here, you had your injectivities were all very low, all below 5, somewhere in the order of 2. And post-acid jumping up to in excess of 20. So in some of these wells, this example was pretty cool because it was all relatively low pressure, old wells, and some of them had declined to the order of 800 barrels a day of production. Not much. And if it was 800 barrels a day, after stimulation, these wells were producing at 2,500 barrels a day. So the payoff of these is quick. Questions for me?
What's generally your limiting factor on your drive-off distance on these jobs? Is it an angle or is it a distance?
It is absolutely an angle, and it's designed by the campaign, right? So if you know your water depth is going to be 1,000 meters, 3,000 feet or so, then we know that the flying lead that we have might be, for instance, 150 feet. So therefore, your departure angle coming from there before they tension up, you want to set your dead man cable to be a certain length that translates to a certain angle of departure before that dead man triggers the ESD. So it's all done by design, and a little bit more into that is the vessel watches its survey plot. So as it has a watch window, it has multiple rings of watch window in 360 degrees. As it starts to drift, it reaches certain rings, and at each ring, you perform a certain operation. So there's a warning, there's a pump shutdown, there is a before the dead man even triggers. It's only if and when the operator is not watching any of those, it finally pulls the dead man and performs it all without intervention. But if you're watching, you're supposed to have triggers and deadlines to perform the disconnects yourself. Please.
Is anyone from the host facility on board the vessel?
Yes, absolutely. The operator is running the job, of course. He will say when certain operations can occur, and he will relay that message back to the host, and the host is aware of every operation that occurs.
How many people does it take on board to do an operation like this?
Great question. In some cases where you have all the liquids carried on the vessel, you have pumping performed from the vessel, dual ROVs, a lot of operations, guys on deck operating, of course, You have your spill response teams on board, you have your fire response team on board, all this additional equipment. We've seen project crews exceeding 90 POB on board a vessel. 92 actually is the highest I've seen. Go ahead.
Are there any concerns about vibration or harmonics as you're pumping down the coil tubing lines down to the unit, or anything you're doing to mitigate that?
Coil tubing is a funny one. A lot of studies are performed on coil, and we typically don't see harmonics occurring due to injection pressures. We see harmonics occurring due to VIV, vortex-induced vibration onto the coil. And in the last few years where you had high current events, loop current events in the Gulf of Mexico, those are things that are watched very closely, and those are studied highly as well. However, so we have an active monitoring system built onto the coil that measures strain on the coil, and as coil is the highest point of strain on the coil is right where you hold on to it on the surface and it deploys. So that point load right there is its highest strain value, and that's where we outfit the real-time monitoring system on there, and it determines it continually determines what the maximum amount of hoop stress you can insert into the coil and the amount of strain you can impart into the coil. That tells us, it's an automatic system, and it allows us to show what the maximum operating pressure of that coil will be. And of course, all of that is analyzed during project planning as well. But very important, coil is monitored very closely, and coil life, that's the term that's used, is monitored very closely. Go ahead, please.
What size coil do you run here? Inch and a half?
Typically it's 2-inch coil, and so those are somewhere in the order of, we tend to clip them for specific projects that really want to optimize the flow rates. But other than that, typically the coil lengths are in the order of 8,500 feet. That's the systems that we have pre-configured. And the flow rates that you're able to achieve through dual coils at 8,500 feet in length into a wellbore with the limits that pumping that you have on the surface typically is in the order of 4 barrels a minute to 6 barrels a minute. And we find that to be good. In the case, and it's actually interesting, in the case of the dual vessel that I illustrated here earlier, in this case here, the operator wanted to achieve, he had a very tall perforation, and he wanted to achieve diversion across the entire perforation, and therefore he wanted a high flow rate. So his goal was 15 barrels a minute, and to achieve that you need a lot of power. So in this case here, we outfitted the vessel with 4 coils. We have 4 coils running through the water column down to the seabed. So if you put that in perspective, a vessel now has 4 conduits coming down to the seabed, 2 additional conduits for ROV, an additional conduit for crane. So you can imagine how many strings you're dangling in the water. It becomes very complex at that point.
And these are your coil units, correct?
Confirmed. Sure.
It's all 10,000-pound stuff or 15?
10 and 15. Recently performing 15K stimulations.